All right, so we're finally ready to finish up chapter 3. With the last topic that we'll be dealing with for this chapter is going to be projectile motion. So we've actually already sort of started talking about this a little bit in chapter 2, but we've only done the one-dimensional case with free fall, right? So essentially with our one-dimensional case, we just had falling objects, which are projectiles, um, but what we did with them was just had their motion constrained to just the vertical component, right? We could throw things up, we could throw things straight down, we could drop things, whatever. As long as their motion was constrained to just that one dimension, that one vertical dimension, that was all we had to do, right? Now we are going to talk about projectile motion in general, right? We're going to do it with two-dimensional motion now, but it's important to understand all of the one-dimensional equations that we have derived are going to still apply to this case, right? We just have to apply them to both the x and the y direction. So again, our projectile is anything, our definition of a projectile is anything that is flying through the air and the only force acting on it is gravity. Of course, in real life, we would have to worry about air resistance and all that kind of stuff. Our model is going to ignore that, and we'll see that it is a pretty good estimate in many cases that we're dealing with, right? To just kind of ignore the air resistance that these objects would experience. So we're just going to deal with projectile motion as though gravity is the only force acting on these. So one thing we can then say right away, what do we still know about our acceleration for these objects? If we have gravity, right, the magnitude of our acceleration is still going to be the same as it was before, right? 9.8 meters per second squared, and the direction is down, right? Down towards the Earth. So this is what our acceleration for all of our projectiles has to be. So really quickly, what can we say? What is then the acceleration in the x direction? If we have an object, if it's flying through the air, right, and gravity is the only thing causing this thing to accelerate, gravity is pulling it down, there is no acceleration in the x direction, right? So there is no horizontal acceleration. So this might seem fairly obvious at first, but it has some possibly unintuitive consequences that we'll get to, right? So there's no horizontal acceleration. As soon as you throw a ball or whatever, as soon as it leaves your hand or whatever it is, you shoot an arrow or something like that. We'll see some examples of all these. The only acceleration is down. So while we are going to be initially launching these objects at some sort of angle, right, that they'll have both a component to their velocity in the vertical direction and a component to their velocity in the horizontal direction. The component of their velocity in the horizontal direction is not going to change for the entire course of the trip, right? So let's go ahead and let's graph this and let's kind of see if we can visualize exactly what's going on. So I'm going to draw a graph. It's going to be a little bit different than the other graphs that we've seen before. So let's draw it a little bit like this. Make sure you can see everything that's going on here. So you'll see the other graphs that I've drawn before when we had our one-dimensional case, I was graphing position versus time. Now what I'm doing is I'm graphing y versus x. So this is just like a physical picture. I'm just going to look at like a side view. Someone is here, they throw a ball, and it takes some arcing path. We're going to look at it like that. So we're not graphing time in this case. We are just graphing like the actual physical path that this ball is going to trace out, right? So if I throw something through the air, it is going to take this parabolic arc, depending on how fast I throw it, and of course what angle I throw it at. It's going to look something like this. So it's not exactly a perfect representation of a parabola, but you kind of get the idea. It's going to be, again, there's acceleration in the y direction, but there is no acceleration in the x direction. So if I map out the velocity of this object over time, and I break it up into its x and y components, this is what it would look like. So here at this point, it's going to have some positive velocity in the y direction, and it's also going to have some positive velocity in the x direction. So these arrows that I'm drawing here, I'm drawing the x component and the y component of this velocity object and I'm going to show you how it changes as it flies through the air. So then it's going to do that. It's going to move on. At some point, it gets to the top of the arc, right, at its very highest point. And at that point, it has no y velocity, right? So there's only acceleration in the y direction. So this, I'm not quite drawing it right, but it's close. This x velocity, right, this component of x velocity is going to stay the same. Then, of course, as it falls back down, right, now it has a negative y velocity, but it has this same constant velocity in the x direction. So you do really get this one object as it flies through the air it is one object, but it is undergoing two-dimensional motion. But you can see that in the y direction, this motion, right? We have our velocity starts out positive, then it becomes 0, and then it becomes negative again, right? This is going to behave just as though in the y direction, if you just isolate what's going on in the y direction, it's going to behave just as though you were to throw this object straight up and come back down. It's just while it's happening, you have this constant motion in the horizontal direction as well. But you can isolate the x and the y, and you can kind of treat them separately. Right? It's important to make sure you understand this is one object, right? So we can separate the x and the y with our equations, but we do want to make sure that we keep track of the fact that this is one object flying through the air. Right? We don't just have two different things doing their own thing here, right? So yeah, so you have this constant motion in the horizontal direction, and you have free fall motion, as we've seen before from chapter 2, in the vertical direction, right? So let's take a look at this. What kind of equations then are we going to be using for these projectile motion problems? Well, we do have two dimensions, so we have to write equations for both the x and the y. Let's take a look at what do my equations of motion look like in the x direction. So if I were to write my delta x equation, I would have v naught x times t, right? So I have my delta x is my initial velocity in the x direction, so my initial exponent velocity times the time, right, which is what we're used to. Then it would be plus 1/2 at squared, right? But what is my acceleration in the x direction? My acceleration in the x direction is 0, right? Again, it's just gravity. There is no horizontal acceleration. Our acceleration is all in the y direction. So you have something that looks like this. This is what I have for the x direction. What can I say about my velocity equation as a function of time? Well, I can say v in the x direction, my velocity in the x direction, is my initial velocity in the x direction. Again, then it would be plus at, right? Plus my acceleration in the x direction times my time, right? So this is all just looking in the horizontal direction. But of course, my acceleration is 0. So this term over here, it would be plus at, but that is also going to be 0. So we have end up with this equation here. It's very simple. It's very obvious. It's not very helpful to us, but it is important to keep this in mind. We're just saying that once we know our initial velocity in the x direction, that's going to be our velocity in the x direction for the rest of our trip, right? So we just this is true, but it's not really going to help us from a problem solving standpoint. You just have to keep in mind you don't have any acceleration in the x direction. So looking in the y direction though, what we can say is this. If I had to write out my delta y, it would look like this. I have v naught y, my initial velocity in the y direction, times t minus 1/2 g t squared. And so I'm writing it for now. I'm just, you can switch it up depending on the problem, and I'll show you some examples where we do both. At this point, I'm just writing this again with down being negative, right, and up being positive. Just have to pick one. That's the usual convention, but again, as we've seen, sometimes down can be positive, and that's just fine as well. So this is my delta y equation. I can also write my velocity in the y direction as a function of time. Very simply, my initial velocity in the y direction minus g times t. And then I can also write, finally, I can say vy squared equals v naught y squared minus 2g delta y. This equation, this other equation that we derived, this will also work. So these equations here, these are pretty much going to be what you're picking from when you are trying to solve these two-dimensional projectile motion problems, right? And again, this one, it's true, right? But it's not useful. You're not going to, I mean, it's just saying, it's just a restatement of the fact that your velocity in the x direction is not changing. So it's really these 4 would be the ones that you would use. But yeah, so again, we have this looks just like what we said for our one-dimensional free fall cases, but now we have added this extra caveat in. We can ask some more interesting questions with this, of course, but these equations that we've been using this whole time will still apply, right? Okay, let's work on some examples for some of these so you can see all of this stuff in action. All right, so our first example that we're going to look at, we can say a ball is thrown horizontally. So make sure we understand what that means. Ball is thrown horizontally from the roof of a 60-meter high building. It lands 100 meters away from the base of the building, right, is what we're saying. So we're standing on top of a building. I can draw a short picture here, small picture. Standing on top of the building, we throw a ball off of this roof, and it initially leaves our hand horizontally, and it's going to land 100 meters away. So it's going to look something like that, right, where we have a 60-meter fall and a 100-meter horizontal distance that we are covering, right? So with this, we want to look at a couple different things. We want to figure out three things. Here's what this problem is asking us. We're going to say, how long was this ball in the air? We're going to say, what was this ball's initial velocity? And we also want to know what is its velocity as it hits the ground. So we want to know what those three things are. So of course, the initial velocity, though, we do need the x and y component. And of course, if we want the final velocity, we also need the x and y component, right? We do need to have both pieces of information about this vector that we were asking for. But first, let's figure out this first one, which is nice and simple. How long was this ball in the air? So let's take a look at that. We know how far this ball has to fall, right? It has to fall down 60 meters. It is going to cover 100 meters horizontally during that time. But does that matter? Does this ball end up staying in the air longer because we threw it horizontally? As it turns out, the answer is no, right? We can treat the x and the y coordinates separately, right? So if I throw this ball horizontally and I do not give it any any initial component in the y direction, basically its initial velocity in the y direction is 0. I can throw this ball horizontally, and if at the same time a buddy of mine standing next to me drops a ball down this with just lets it go, they don't throw it in any way, shape, or form. As long as I throw it horizontally and I don't give it any y component of velocity, at the exact same time someone drops a ball, we ignore air resistance. The ball that is thrown will travel much further than the ball that is dropped, but they will actually both hit the ground at the exact same time, right? So again, no acceleration in the x direction, so the fact that it's traveling in this constant motion in the x direction is not going to affect what is going on in the y direction. So let's go ahead, let's look at our equations that we have. Let's solve for what this time is. Well, I can write right away. I can say delta y is going to be equal to 1/2 g t squared. In this case, I'm just going to put it down as positive, right? We're not having this ball go up and then down or anything like that. So I'm just going to put it down as positive. It's 60 meters high. So what is our delta y then? Our delta y is 60. Our acceleration is 9.8. And our time is what we're solving for, right? So again, this is the exact same equation that you would write if you just dropped this ball off the roof of this building. We threw it horizontally, but in both cases, the y component of velocity is the same. So the initial y component of velocity is the same. The acceleration is the same. We just have the 60 meters that we're going to fall. And so we can very simply solve for our t and figure out what that is going to be. You can drop a ball and you can throw a ball horizontally at the same time, and they will both hit the ground at the same time. So we do our algebra. T is going to be the square root of 2 times 60 meters, right? Delta y is 60 divided by 9.8 meters per second squared. You do this, and what you should get is a time of about 3.5 seconds. So this is the first part. We have that. We also now want to know what the second question that we have is, what was this ball's initial velocity, right? So how can we figure out what that one is? Well, we already have figured out something, right? We've already implicitly stated, okay, just by writing this equation, when we don't include that v naught y times t term, we know that it's because it must be 0, right? V naught y is 0. We threw it horizontally. The y component is going to be 0, then in that case the initial y component. So the initial velocity is all going to be determined by what the initial velocity was in the x direction. So let's write our delta x equation and see what we get. So delta x equals v naught x times t. No acceleration in the x direction. This is nice and simple. In the horizontal direction, again, we just have a very simple distance equals rate times time problem, right? We know how far it went. It went 100 meters. And so we can solve for our v naught x. We know the time now from part 1. So we have v naught x is going to be equal to 100 meters divided by 3.5 seconds. And you get a initial component of your x velocity as 28.6 meters per second. But of course, again, we already know v naught y has to be equal to 0. So here's my x component, here's my y component, and that's it. That's all I had to do to figure out the initial velocity. Again, this is what's called a zero launch angle problem. Basically what we mean is we're launching this projectile, but we are launching it at an angle of 0 degrees above the horizontal, right? We are throwing it horizontally. So for all these problems, the initial velocity is also the initial x component of the velocity, right? Because there is no y component. Okay. Let's use some of this stuff. Let's figure out what was its velocity as it hit the ground. So how can we figure out what this one is then going to be? So if we need to know the velocity as it hit the ground, again, we have to know both the final x velocity and the final y velocity. But of course, what is the final x velocity? It is also the initial x velocity, right? No acceleration in the x direction. This one has to be the same. So the final in the x direction is just v initial in the x direction is just 28.6 meters per second. Now we can have to have one more equation to figure out what our final velocity was in the y direction. So we can say this, we can say v final in the y direction is going to be v initial in the y direction plus g times t. Again, I'm just putting down as positive, so it'll be positive 28.6 meters per second and then positive whatever this happens to be. What is our initial y velocity? It's 0. So we have v final in the y direction is just simply it accelerated at a rate of 9.8 meters per second squared in the y direction, and it accelerated at this rate for 3.5 seconds. And so it hit the ground with a vertical component of its velocity of 34.3 meters per second. So this would be enough information, right? We have 28.6, we have 34.3. We can go ahead, we can do our practice here. Our speed that we're going to hit with, then take the use our Pythagorean theorem to figure out what our overall speed is that this ball hits the ground with. We have vx squared plus vy squared, and we should get is about 44.7 meters per second. And then the angle that this hits at, again, we didn't specifically ask for it in the problem, but I'm just going to go ahead and show you how to do it just in case, equals the inverse tangent of vy over vx. In this case, again, vy is your 34.3, vx is your 28.6, and what you should get is about 50.2 degrees. And this is 50.2 degrees below the horizontal, right? So we know it's going to come down. If I look at this picture that I drew up here, right, it's hitting the ground, something like that. This is the angle that I solved for here, below the horizontal, right? Again, it was because I called down positive, so that's okay. Just make sure you keep track of when you're if you are going to solve for an angle or something, and you've already decided that down is positive, that's fine. Just make sure you understand and keep track of all that stuff. So that basically gives you everything that you want to know about this one, right? We figured out it was launched horizontally, right? And what we were able to see right away is that launching something horizontally, as far as when it hits the ground is concerned, is going to be the exact same as dropping something, right? You can do this, you can set this experiment up if it seems a little bit strange to you at first. You can, you have to be precise about it. But yeah, throw a ball horizontally. If you actually throw it straight, you drop one at the same time, they will hit the ground at the same time, right? That extra horizontal velocity that you give the one that you threw in the horizontal direction, that x component of velocity doesn't affect how long it takes to hit the ground, right? That doesn't affect what is going on in the y direction. All right, let's go ahead and let's look at another problem that we then have. So we're going to say, in this case, we're going to have a ball is kicked with a speed of 16 meters per second horizontally and 12 meters per second vertically. So now we do have this case where we have projectile motion, but we don't have a zero launch angle. We are launching at some kind of angle here, right? We're launching, we have both the x and y components of our velocity initially, right? We have those both as this projectile is launched. So then we can say, with what speed does the ball hit the ground? We can also say, how long is it going to be in the air? And we can also say, what is the maximum height that the ball reaches? So one thing I can actually assert here really quickly, we can say is this, right? We can say, what speed does the ball hit the ground with? And here's what I'm going to do. I'm just going to solve for this right away, and I'll explain what I'm doing here in a second. I'm just going to figure out what is the speed this object was launched with. Right, I have my x component, I have my y component. Do your Pythagorean theorem, x squared plus y squared, square root of that gives me my overall launch speed. But In this case, we don't have anything about this ball not being launched on level ground, right? So we can go ahead and it's safe to assume we are, this ball's going to land at the same height that it started at, which in this case, just based on the symmetry of the situation, I know the horizontal component is not going to change. I know that the vertical component, well, if it goes up and ends up back up at the same height that it started at, right? The y component, it'll start at 12, it'll slow down due to gravity. As it gets to its maximum height, it has a 0 then component for its y velocity, but then it will accelerate over that same distance, that same vertical distance back down, and when it hits the ground, it will again be moving at 12 meters per second now in the negative vertical direction, right, downward. So in other words, what I'm saying is since I launched this ball on a level surface, the speed that it lands with is going to be the same as the speed that it is launched with, right? You can go through, you can do the math yourself if you want. You can figure out, how long this ball is going to be in the air. You can figure out, that you can use your delta y of 0, and you can solve for all these different things. You can try and figure out what this final component of your y of your velocity in the y direction is going to be. But what you will see, just based on the symmetry of the situation, we're launching on level ground. It goes up a certain height, it comes back down a certain height, and that speed that it is going at in the vertical direction must be the same speed that it left with, right? It went 12 meters per second up. When it comes back down, it will be moving at 12 meters per second down, and so it will land at the same speed that it was launched with, right? So the next thing that we do want to know is how long was it in the air? So let's figure out exactly how we can go about doing this one. So we can actually, in this case, what do we know? We have our delta y equation that we can use for this one. We can say delta y equals v naught y times t minus 1/2 g t squared. In this case, this will work, right? What is our delta y in this case? Our change in position in the y direction must be 0, right? It must actually be equal to 0. Again, we go up and we come back down. We land at the same height that we started at. Our v naught y we know is 12 meters per second. We don't know t, but we can solve for it. And we also can figure out what g is, right? Well, we don't need to figure it out. We already know. We're on Earth. We're assuming that we're kicking this ball on Earth. And so this g will be 9.8 meters per second. However, if I do this, though, you'll see I have to do the quadratic formula, right? X equals the opposite of b plus or minus square root b squared minus 4ac all over 2a. I can do that with this equation here, keep track of what these are. Or I can do it a little bit simpler. You can actually see that this is going to, since this is 0, I can also just start canceling some stuff out and figuring out that way. Or there's another way that I can do it. Yeah, so I can write it like this. I'm gonna show you a couple different ways to do this. So we have 0 meters equals 12 meters per second times t minus 1/2 9.8 meters per second squared times t squared. I can actually cancel out a factor of t in this case. And what I get is then this equation here. So we would have 0 meters equals 12 meters per second minus 1/2 9.8 meters per second squared times t. You can solve for t in this way, which will equal what? So we'll move this over. We would have 12 times 2 is 24. The negative signs would cancel out. You'd have 24 divided by 9.8 meters per second squared. So this is how you would get there using your delta. Whoops, I've been off the screen for a little bit here. Sorry about that. So you can say, okay, we started with delta y equals v naught y t minus 1/2 gt squared. You can then cancel out the t's, right? Just divide everything by t. 0 divided by t is still 0. And so then once you have that, you have one factor of t, which will also make things simpler. Move the 12 over, multiply by 2, and then you get divide by 9.8. T equals 24 meters per second divided by 9.8 meters per second squared. This also is equivalent to using your velocity formula. You actually get the same thing as what you would hope, right? So let me just show you the other way to do it. You can figure out this time using your delta y equation. You can also figure out this time by using this equation. You say v final in the y direction equals v naught in the y direction minus g times t. So what is my v final in the y direction? I already told you from this part, right? It must be negative 12 meters per second equals positive 12 meters per second for the initial velocity minus 9.8 meters per second squared times t. And so then when I do this and I move this over, you'll get the same thing, right? I have negative 24 meters per second equals 9.8 meters per second squared times t. Solve for t, and sure enough, sorry, this is a negative sign. I don't want to lose that. Negative signs will cancel out though. That's why it's important that I include it. So we do get a positive time. So of course you get 24 meters per second divided by 9.8 meters per second squared. So this is starting from two different formulas, our delta y equation or our final velocity equation, but of course we do end up, if you cancel out this t here, they do simplify to be the same thing. So in this case, our t will just be, what is that? Just simply 2.4 seconds, right? So yeah, so this is again two different ways to, I mean, you get the same answer, of course, but either equation will get you to the same spot, right? If you want to do it in terms of knowing what the delta y is, or if you want to do it in terms of thinking what the final velocity must be for this problem. Either way, of course, as you would expect, they do give you consistent answers, consistent results, which they should. Your t is 2.4 seconds. All right, what is our last question that we have? What is the maximum height that the ball reaches? Okay, this also has a couple different ways to do it. I'm going to show you one of them and I'll kind of talk about the different ones. Okay, so how do we figure out what is going on with this ball at its maximum height? So one thing we can do, since we're on level ground, is we can assert that the maximum height, right, let me draw a little picture here. If I'm looking for the maximum height, I'm kicking this ball on level ground, and it does that. Right here, this is halfway through my journey, right? So I can say on level ground, my maximum height will occur after half of my total time has passed, right? We're saying the total time that the ball's in the air was 2.4 seconds. Right in the middle, though, will also be the maximum height, which would be at 1.2 seconds, right? That's one way you can do it. There is another way you can do it, though. This method only works if you're on level ground, saying that the maximum height happens at 1/2 of the time, right? The other way that you can do it that will always work is to think about our diagram that I showed you when I graphed out what this stuff was. Let me come back to this for a second here. Let's look at this graph here. What is going on in the y direction at the maximum height? This one is true all the time. We can see that the y component of our velocity must be exactly 0, right? If the y component of your velocity is exactly 0, and you are undergoing projectile motion, well, you're only going to accelerate down. So once it's actually 0, that is going to be your maximum height, right? If you still have some vertical component of your velocity, it means you're still going up, right? That's what that means. However, when you see that the vertical component of your velocity is exactly 0, that is the condition that will always give you the maximum height, regardless of whether you're launching on level ground or not. And of course, the next problem I'll show you where we have a projectile not being launched from level ground. So let's look at this again. Max height happens when your y component of your velocity is 0. So let's go ahead. Let's now set up our equation and solve for that. I think the best way to do this would then be to use our velocity equation that relates our final velocity, our initial velocity, our distance, and our acceleration. So when you're solving for max height, the one that you want to use would be this. Velocity in the y direction squared equals initial velocity in the y direction squared, in this case, minus 2g delta y, right? So I'm still defining down as negative this time instead of positive. So what is our final velocity? Now we want to set the condition to be our final velocity of 0, right? And then that will correspond to when we are at our highest point. So this will be 12 meters per second squared minus 2 times 9.8 meters per second squared times delta y. And so this delta y now will give you the maximum height, right? We have set up our equation such that the condition we want to fulfill is when we have 0 for our maximum height. So we have 0 equals our initial speed squared in the y direction minus 2g delta y. Solve for delta y. Run out of room on my paper here. Delta y in this case will equal 12 squared is 144 meters squared per second squared divided by 2 times 9.8 meters per second squared. And what you get is a maximum height of 7.3 meters. So yeah, again, maximum height in general. If you have it on level ground, you can see how far it's gone after half the total time. That's acceptable to do. But in general, I think this is the better way to do it. You're not always going to be on level ground. So keep track of when is your y component of your velocity going to be equal to 0. And that will also tell you when your object is at its maximum height. Okay, we've got one more example that we'll go through. That's a little bit more complicated than these other two. But we'll kind of see some other properties of how we can solve these problems. So in this case, we're going to say we are now not on level ground. We're going to say an arrow is shot from a height of 1.5 meters to the top of a cliff with a height of h. So we don't know how tall the cliff is, right? The cliff's height we're going to call capital H. The initial velocity is going to be have a speed of 30 meters per second, and it's going to be launched at an angle of 60 degrees, right? And we're going to say that it hits the top edge of the cliff 4 seconds later. So now we have something that looks like this, right? We're launching our arrow from about 1.5 meters up. It's going to come up and it's going to hit the top of this cliff here. And so we know everything there is to know about our initial velocity, right? So this is what our picture looks like for us launching this arrow. We're launching it from some height. There is a small height here, small height difference, as we are standing on the ground with this arrow. We're not shooting the arrow from the ground itself. So it's launched from 1.5 meters above the ground. It's launched at a speed of 30 meters per second at an angle of 60 degrees. And it's going to hit the top of this cliff of height h 4 seconds later. So the first thing we want to know is how high is our cliff? After that, we also want to figure out what is the maximum height attained by the arrow. We'll use that same trick we did last time. And we can also say what is the final speed of the arrow as it hits. So let's figure out this first one first, right? How high is our cliff? So we can say this. We know, let's write our delta y equation for this, right? We don't know what this delta y is, but if we do know what it is, we can figure out what our h must be, what the height of the cliff must be. So for our arrow, we can say delta y equals v naught y times t. We do know the t, so that's going to make things simpler for us, minus 1/2 g t squared. So how can we write this delta y? Well, the delta y is going to actually be this. It's not quite just going to be the height of the cliff, right? The cliff is some distance up. It's this distance h, but we launched this arrow from 1.5 meters above the ground. So the arrow is really traveling. The final height that the arrow ends up at is h. The initial height that it started at is 1.5 meters. So our delta y, I'm going to substitute in h minus 1.5 meters, right? This is then going to equal what? So this is our delta y. Now our v naught y is going to be this, 30 meters per second times the sine of 60 degrees, right? So we have this. We're going to just think about our trig that we have to do for our vectors. We have our the length of our vector of our velocity vector is 30 meters per second multiplied by sine of 60 will give us the initial component in the y direction, right? Then we have minus 1/2 g t squared, and the g is again just going to be 9.8. So solve for h. We can just very easily do it this way. 30 meters per second times sine of 60 degrees minus 1/2 times 9.8 meters per second squared times t squared. Whoops, don't want to forget my factor of t here. I've been leaving that off. And t is equal to 4 seconds, right? So we know this, right? We know everything to know about our initial velocity. We know the time. We know our acceleration, and of course we know the time. So at this point we can simply plug everything into our calculator, and we get this. H in this case is going to be about, whoops, also leaving off this factor of 1.5 meters, right? H in this case is going to be about 27 meters. So this is the height of our cliff, right? Delta y, where we ended up, where we started, minus where we started. Our initial speed, we have to break it up using our trig. We have our acceleration, we have our time. So we can plug that all in. We get a height of 27 meters. So now the next thing that we want to know is what is the maximum height attained by the arrow. So let's do that same trick again. In this case, we're going to say our v final in the y direction squared equals v initial in the y direction squared. And we also want to say minus 2g delta y. Let's plug our values in this case. For our maximum height, again, this delta y will correspond to our maximum height. If we set our final speed to be 0 meters per second, our initial speed is again what it was before in the y direction, 30 meters per second times the sine of 60 degrees squared minus 2 times g times delta y. G is again 9.8. Delta y is what we are looking for. So we can have this, we say delta y is equal to 30 meters per second times the sine of 60 degrees squared divided by 2 times 9.8 meters per second squared, and we end up with a height. Don't forget to square this velocity here. You should end up with a maximum height of about 34.4 meters. Okay, and then the last thing that we want to say is what is the final speed of the arrow as it hits. All right, well, we already know what our final speed in the x direction is going to be, right? It's going to be the same as it was at the beginning. It's going to be our v naught times cosine of 60, right? So in the x direction, we have v final x equals 30 times cosine of 60 degrees, and this is in meters per second. That will be our v final in the x direction. For v final in the y direction now, after we've gone through the entire course of the trip, what do we need to do for that one? So v final in the y direction, we can just use our velocity as a function of time equation. We have v naught y minus g times t. This is again 30 meters per second times the sine of 60. Running out of room. We'll be okay. Final y equals 30 meters per second times the sine of 60 minus 9.8 times t. This is still 9.8 meters per second squared. This t is still 4 seconds. We get a final velocity in the y direction of negative 13.2 meters per second. I'm going to actually go up to work to finish this problem out. So we have our overall final speed will look like this. Square root of our x squared minus our y squared. So 30 times cosine of 60 squared plus negative 13.2 squared, and what you should get is a final speed of about 20 meters per second, right? So that's what our final speed of our arrow is right as it hits the top edge of this cliff that we have here. So again, this is just kind of a more general problem that we have. We're given, in this case, our initial speed and our initial launch direction. With that, we can break our initial velocity down into its components. From there, we can figure out how high the cliff is. We can figure out the maximum height, again, by keeping track of the trick of using the fact that we know that at the maximum height, the y component of the velocity must be 0. And of course, we can find the final speed of the arrow as it hits, keeping in mind that the initial velocity in the x direction is going to stay the same. So we only need to figure out what the final velocity in the y direction is, and then do our Pythagorean theorem to get our 20 meters per second.